Roughly speaking, undergraduate degrees in the UK have 2 years of core material followed by 1 year of more specialised material. In the US, the more specialised material is typically postponed to graduate school. The UK may be going the same way, because the dumbing down of A-levels is now so severe that most physics students arrive at university with negligible knowledge of physics. It's a curious fact that the core syllabus has not changed much since I studied at Cambridge University at the end of the 1960s. Indeed, the last major overhaul of core physics was arguably the Feynman Lectures on Physics, 3 volumes based on Feynman's lectures at Caltech in 1961 and 1962. Incidentally, if you're thinking of buying it, I recommend getting a second-hand copy of the older red edition. The only significant changes in the new blue edition are in the 4th volume of exercises, which is worth getting. For those not familiar with him, Dick Feynman, 1918 to 1988, was one of the more famous physicists in the 20th century. He got a Nobel Prize in 1965 for his work in devising a quantum field theory for the electron, but others got there almost simultaneously and shared the prize with him. His most important work was probably the Feynman diagrams, a technique for organising calculations in quantum field theory, which made them far shorter and easier. The reason he became so well known was because he also had a gift for communicating. He wrote 2 uproariously funny memoirs. Which have sold more, as well as some more technical books. The most famous of these are the Lectures on Physics, which have sold more than 1.5 million copies. Interestingly, it was not actually written by him, and differs significantly from the audio recordings which became available a decade or so ago. The rest of the faculty at Caltech pitched in with many minor revisions and improvements to the spoken lectures. A great deal has happened since 1962, so it is perhaps surprising that the way core physics is taught today has not changed much. In fact, we are way overdue for someone to wade in with another major overhaul. Feynman's written lectures are not arranged in quite the same order as he delivered them. After 2 lectures of general introduction pointing out the centrality of the idea of the atom and giving some brief history, Volume 1 has 21 lectures on Newtonian dynamics, including 2 on special relativity. Then come 11 lectures on optics, without much quantum theory, 8 lectures on the kinetic theory of gases and thermodynamics, 4 lectures on sound, 1 lecture on waves, and finally an introductory lecture on symmetry. Volume 2 has 36 lectures on electromagnetism. Most of these are fairly conventional, but there are a couple of less conventional ones, one on vector potential and the other on the principle of least action. Then there is 1 lecture on crystals, 2 on elasticity and 2 on fluid dynamics. Volume 3 has 21 lectures on quantum theory. Here the presentation was groundbreaking. There is only 1 lecture on the Schrödinger equation, which is the usual mainstay of a first course in quantum mechanics. And he manages to convey several more advanced topics without ever introducing any formal development of quantum field theory. So Volume 3 was revolutionary. Volume 1 had many innovative details, but Volume 2 was largely conventional. His major critic has been Carver Mead, who later joined him on the faculty at Caltech. Mead complains, correctly, that Feynman should have done more to update the approach to electromagnetism. Mead eventually came out with a book called Collective Electrodynamics, Quantum Foundations of Electromagnetism, a slim volume of 160 pages, which sketched out the rudiments of what he saw as the correct way to approach electromagnetism. Unfortunately, he never completed the project, or at any rate hasn't yet, of elaborating this into a full-blown treatment. However, one can go further. What, in principle, should the core syllabus include today? Leaving practicalities aside for a moment, what would we like to include? There are now 2 fundamental theories in physics, the Standard Model and Einstein gravity. We would certainly like to include those. They're usually considered too difficult for undergraduates, but that is not really good enough. Researchers have 4 jobs: discovering new results, distillation, scholarship, and teaching. Unfortunately, the emphasis today is mainly on the first, with a gradually increasing emphasis on the last. But you cannot teach what has not been distilled. We can only stand on the shoulders of giants when we have managed to distill their results into undergraduate lectures. Scholarship, incidentally, for the benefit of those wondering, means a familiarity with what others have done, preferably to the extent of being familiar with the key original papers and not just in some narrow specialism. So we have to figure out how to distill quantum field theory and its major fruit, the Standard Model, into a few undergraduate lectures, and similarly for Einstein gravity. In both cases, this also means covering experimental verification. Unfortunately, to say that CERN has not yet complied with best practice on reproducible research for big data is a considerable understatement. At the moment, one has no choice but to dismiss the Higgs boson as speculation or to accept it on faith. In fact, one probably needs 2 or maybe 3 lectures to distinguish adequately between the parts of quantum field theory which are solidly established and those which are not. The case of gravitation is slightly different. There is ample evidence for the truth of Newtonian gravitation on solar system scales, and for the small differences one obtains by applying Einstein's modifications. But the situation is entirely different when it comes to astrophysics. Almost all the evidence from the motion of stars in galaxies and galaxies in clusters is against both theories. This is hardly surprising, because the data on which the theories were based was almost entirely derived from the solar system, where the gravitational field is around 1 billion times stronger than in the galactic cases. It is hard to think of any case where a theory developed on data for one scale remained largely unchanged when one looks at scales different by such a huge factor. Nevertheless, there has been huge resistance in the astrophysical community to modifying the theory of gravity. The reasons for that would take a whole lecture, but it is certainly true that one reason is that no one has yet come up with a convincing alternative, mostly for want of looking. Fashion has imposed an unfortunate catch-22 situation. The apparent failure of our gravitational theories in the weak field domain is certainly one of the 2 most important problems in fundamental physics today. The other is that quantum field theory and the theory of gravity appear to be incompatible. Roughly speaking, quantum theory predicts that empty space will be full of particle-antiparticle pairs fluctuating in and out of existence, and gravitational theory then predicts these pairs will have a substantial gravitational effect which is not observed. Equally important, quantizing gravity has proved exceedingly troublesome for the theorists. Work started in earnest about 50 years ago. Back then it was known as supersymmetry. As we will explain later, the fundamental forces of nature, electromagnetism, the weak force and the strong force, can all be regarded as arising from symmetries. So the idea was to add an additional symmetry to bring in gravity, hence supersymmetry. This has now been developed into string theory. Unfortunately, it has so far wholly failed to justify the substantial intellectual resources that have gone into it. Its only apparent contact with data is that it predicts a vast array of new particles, none of which appear to exist. The rather feeble response of the theorist is that they only fail to exist near the Earth. The rest of the universe could be knee-deep in them. Well, the justification for that is apparently that they could make up the missing matter presumed to be necessary to explain why gravity on galactic scales is so much stronger than we expect. But there have been no serious attempts to make that quantitative or to generate testable predictions. The same theorists are often also engaged in devising theories for the early universe. That is a bizarre enterprise. Almost all our data from the universe comes from light. Light has a finite speed, so as one looks out into space, one is also looking back in time. As telescopes have got better, we can now look back billions of years. The critical data was first collected by Hubble in the 1920s. He realised that light from the distant universe was redshifted. In other words, its wavelength has lengthened, and the further away the source, the greater the lengthening. The only previous encounter with redshift came from the Doppler effect. Light is redshifted if the source is moving away from the observer, so it appears that the universe is expanding. Further work suggested that the expansion was rather like that of a cake in an oven. The whole cake expands, so the distance between any 2 raisins in the cake increases by an amount proportional to their distance apart. If one runs the process backwards, the universe apparently emerged from a single point source something over 10 billion years ago. That, briefly, is the Big Bang theory. The evidence for it is both complicated and weak. The complications come from the difficulty of collecting reliable astrophysical data. Objects any distance away are typically seen through clouds of dust and clouds of ions, with the light bent by stars and galaxies close to the path of the photons. Then the key data is the redshift, but that has 2 components, one due to the general expansion of the universe, and the other due to local motions of a star moving around a galaxy, for example, or a galaxy moving around another galaxy. With a few exceptions, disentangling those 2 can only be done statistically rather than precisely. The other problem is the so-called surface of last scattering. The further back in time you go, the denser and hotter the universe was. In fact, the theory implies that at 0 plus 100,000 years, it was so hot and dense that photons were scattered all over the place, rather like those emerging from the centre of the Sun today. They can take an amazingly long time to reach the surface of the Sun because of all the scattering. By the time they do, they are randomized and no longer convey much information about conditions in the centre of the Sun. Similarly, photons coming to us from times before 0 plus 100,000 years carry little useful information. But the theories of the early universe are typically all about what happens in the first split second. We cannot image that early or get any kind of detailed data about it because of all the scattering. All we can measure are maybe half a dozen numbers which broadly describe characteristics of the more recent universe. The snag is that the theories of the early universe have a similar number of free parameters. In other words, all one gets out of an immense amount of hard work and computation and an immense amount of expensive collection of data, is the ability to twiddle half a dozen or so free parameters to fit half a dozen or so, quote, constants derived from expensive astronomical observing programs. The theories predict absolutely nothing. This is not science in the normal sense, it's just parameter fitting. It gets worse. The correct role for the theorist, as great theorists like Feynman have always acknowledged, is to dream up theories with few free parameters which make definite, disprovable predictions. Collectively, their job is to make sure there are always at least two theories in any area of current interest. Then the experimenters have a target to aim for. Their job is to devise experiments which will distinguish between the theories and prove at least one of them wrong. The Big Bang Theory was the collective work of half a dozen theorists, including Fred Hoyle, 1915 to 2001, who was far and away the greatest astrophysicist to date. He was largely responsible for the theory of how stars work, which is the great gem of astrophysical theory. He knew that one cosmological theory was not enough, so with a couple of collaborators, he dreamed up another, the steady-state theory. The idea was that small amounts of matter are continuously created, at a rate far too small to be detected directly, but enough to maintain the density of the universe constant as it expands. A colleague at Cambridge succeeded in disproving that theory. Distant galaxies turned out to look quite different from nearby ones, whereas the steady-state theory predicted that they should be similar. Unfortunately, the Cambridge tradition of debate bordering on the acrimonious resulted in Hoyle leaving Cambridge to work as an independent researcher, funded by his book income. In 1992, he came up with another alternative to the Big Bang, elegantly set out in a series of papers. Disgracefully, these have been universally ignored and Hoyle dismissed as a crank. So, that is the second major challenge of updating core physics. Astrophysical and particle physics data have become abundant since the Feynman lectures, far too abundant to ignore. But a good deal of care is needed in distinguishing the resulting theories. Some are well established, some are wild speculation, others are useful but tentative hypotheses. There is a third challenge. We need to cover substantially more than just the two fundamental theories. As Brian Pippard was fond of reminding his colleagues, there is little point in knowing high-flown theories if you cannot carry out basic calculations. That is why the Cavendish problems on physics remain popular in the Cavendish lab today. We look at the third challenge, updating the range of less fundamental material, in the next lecture.